Up until now, every time I've asked you to find the derivative of a curve, you've been able to do this easily. And the reason is that you've always been able to get y as the subject of the formula. This is called explicit differentiation. In the example that I've given you over here, you can see that y is the subject of the formula. So if I want to find the derivative, I would have very easily been able to work it out by saying that dy by dx is going to be 2x. But what would happen if I could not get y as the subject of the formula easily? Take a look at the example I have on the screen now. You can see that y is not the subject of the formula. Now, because it's y squared, I could probably have said that that means that I have that y is going to be plus the square root of x cubed, but it is also going to be minus the square root of x cubed. If I'd wanted to find the derivative, I would have had to find the derivative of both parts of this curve, and that seems like a lot of work. Because of this, mathematicians have worked out another way, and this is called implicit differentiation. So if I'm not able to get y as the subject of the formula easily, I'm going to follow the following method. Clearly, it stands to reason that I still want to find the derivative in the variable of x of the left-hand side of this equation, and I must find the derivative in the variable of x of the right-hand side of this equation. The right-hand side is the easy side because the expression is in the variable of x, and that is the variable that I want to differentiate. Using the power rule, I find that the derivative of x cubed is 3x squared. But this is not so easy on the left-hand side. If I look at the left-hand side, my expression is in y, but I must differentiate in the variable of x. We're going to do this using the chain rule, and all you have to understand at this stage of your career is the mechanics of the rule. In other words, what I'm going to do is I'm going to find the derivative of y squared in the variable y, and I'm going to times that by dy dx. The first factor on the left-hand side can now be differentiated because the expression is in the variable of y, and I want to differentiate y. In other words, I'm going to have 2y, and that must still be times by dy dx. Still making that equal to 3x squared, you should be able to see now that if I take dy and by dx, and I divide both sides by the factor of 2y, I find that the derivative of that curve is going to be 3x squared, all divided by 2y. In other words, we've been able to find the derivative of this equation very easily by using a new method. This method is called implicit differentiation. The one big difference to the previous form of differentiation and implicit differentiation is you now can see that your derivative is going to use both the x and the y of the point of contact of my tangent.